All right, welcome back to Stat 3050, the University of Wyoming, and we're looking at regression. We're looking at how our models are doing. We've made a new model. We're looking at just as a recap. We are looking at let's see. I think it's density. I don't think I know. It's density and age, and it looks something like this. Okay, and we have our points around like that. But what we want to do now, we want to figure out how our model is doing. And we do that by looking at what's called residuals. And we have a few assumptions with linear regression too that we want to make sure are true. Some sort of requirements. And so if you listen closely, you can hear a wood chipper in the background. I can't stop that. I have my window open because it gets too hot in my office. So just, maybe we could do some sort of regression on the amount of noise and in the background and how it affects my teaching here. Hopefully the slope is 0. All right, so what do? Well, we have these assumptions. We have some requirements of linear regression that we need to make sure are met before we can do anything with the model, before we can actually say that the model is okay. And so the first sort of, not so much the first, but like the kind of like the 0th assumption is making sure that the variables are, and this is a long word for me to spell out, so just give me a second, meaningfully, good Lord, numeric. All right. Writing with my finger, for those of you who are new, just know that I don't normally write like a child, but it is, it's not too much different than this, but whatever, it's not too important to harp on that. Don't send me emails. So anyway, so what do we mean by meaningfully numeric? Well, let's say that, so here's an example. Let's say that we're working with some kind of regression, some kind of data, and we have, in one of our columns, we have something that represents colors. And we have one coding the color blue, we'll say. We have 2 coding the color green. And we have, 3 coding the color red. Well, we know that these variables, these numbers here represent something else. They represent some color. But the computer does not know that. So if it were to add 2 and 3 together, that would be 5, right? 1, we don't know what color that would be because that's not exactly what we're doing, right? We have no clue. But the computer thinks, oh, okay, it's going to be 5. The numbers actually mean something. The numbers are actual measures of something. And so we know that that is not necessarily the case, right? So it's okay. We'll talk more about how we can kind of deal with this sort of coding scheme. But for right now, just make sure that everything is an actual measure of something. All the numbers actually represent some measure of something and not some kind of coding scheme. All right, so that's okay. We're good there. Well, and then we have 3 other assumptions, and these are the 3 main assumptions. We have this idea of goodness of fit, where the data and the residuals must appear linear. Well, what do we mean by that? Well, I'll show you in a second. But typically, we're fitting a line. We're fitting a line to the data, and we want to make sure that that line and the data are pretty similar, right? We don't want to have a straight line going through data that looks like this, right? Not good. So we have ways of fixing that, ways of modeling that, but for right now, we need to make sure that the line fits the data well. And then we have this other idea, this fun word called homoscedasticity. Well, what does that mean? It's a fancy word for just saying equally scattered. And I'll show you in a couple of slides what that looks like. So just keeping in mind that this fancy word really more or less is just saying how scattered everything is when we plot it. And I'll show you what that looks like in just a second. Okay, and then we have our normal distribution, and the residuals must be normally distributed. And so I'm going to use this sort of fancy notation here, 0, 1. This is a 1. It's still a 1. But we know that this capital N normal, and then the mean is 0, right? And then the standard deviation is 1. So it would look something like this, where the distribution is centered at 0. Typically, it's just a measure of distance between the fitted and the observed value. But we know that the normal distribution looks something like this. So just keeping that in mind, we should see a histogram and other figures that represent sort of a normal distribution. Okay, so another thing, before we get too hung up on all of this, we sort of treat the assumptions here. This one is the most important. Well, yeah, for sure. This one is the most important. You can't do regression if your values are not meaningfully numeric. But when we see this goodness of fit, we are making a straight line on the data. We need to make sure that is true, right? Because then after that, let's say that this is not true. We don't even care about the other two assumptions. We're not even going to worry about them because we know the first one isn't good. Let's say then, whoops. Okay, so let's say then that we have goodness of fit. Goodness of fit assumption is good. And then we're looking at the homoscedasticity. And we see that there is not equal scatter. There is no equal scatter in the residuals. Well, I'm not even going to worry about looking at the distribution of the residuals because I know it's going to be kind of funky since the homoscedasticity is not there. So we sort of do it in this order. We always sort of go 1, 2, 3 in checking. It's especially important that we do that because sometimes the distribution can still look a little normal, but there's no goodness of fit, or there's no equal scatter, right? Typically, that's not always the case, but there are some situations where you'll find, the distribution looks okay, but really the overall scatter of the thing is not great. So just keeping that in mind, we always go in order here. All right. So let's take a look. Well, goodness of fit, easy peasy, right? We see here. Let's look here on the left. We see, the data are pretty scattered, right? But that line fits them pretty well. You don't see any sort of evidence of curvature or anything like that, right? So this is probably just some data set, right? This is not the residuals. But we look at the data and the residuals for the goodness of fit in a simple linear regression. So just a kind of a recap. This is our simple linear where we only have just one predictor. The data and the residual plots will look pretty similar. They will look pretty similar. So just keeping that in mind, we're looking at goodness of fit. We're looking at whether or not a line fits the data well, a straight line. And we see that is especially true here, right? So if we were to draw sort of like 2 additional lines equal distance away, above and below, we sort of see that most of the data hangs out in that kind of gap that we've made in this sort of region here. So that's good. Well, what does poorness of fit, a poor fit, look like? Well, this is what it looks like. So we've got sort of these data here that are very obviously curving upward, right? Not good, not good. This straight line that we have is legitimately calculated but not doing a good job. It's saying that the fit here, if we were to have an x value of 3 in this case, trace it up and then trace it over, it would be somewhere around like this 5 or whatever. But in real life, we know that this residual is going to be super big, and this is what it's actually representing over here on the y. So just keeping that in mind, right? You can calculate straight lines legitimately, but sometimes they do not do a great job. And we see sort of the same situation over here. We sort of see this like almost polynomial kind of curve. This would be, some sort of like something that looks like this. I'm going to leave out the beta coefficients just for now. Oops. Just for now, leaving out the beta coefficients, but it would look something like this. Very confusing to interpret. Overfit, we'll talk about overfitting plots, or sorry, overfitting models. But for right now, we know that this line, this straight line here, is not doing a great job. The residuals would be all over the place. All right. So then we have this idea of equal scatter, this homoscedasticity. Boy, it's a big word. But this is a good example of what homoscedasticity equal scatter should look like. So how do we determine this equal scatter? We're going to be doing everything in this class, for the most part, visually, okay, when we're looking at these assumptions. So what I do, sort of in my head, and I can do it now since I'm drawing, when I make these sort of bins here, about the same size, and I sort of eyeball and I say, okay, it looks like most bins have the same number of points in them. You don't want to get too small, right? But this is okay too. So just sort of seeing like, okay, it looks to me like most of the bins have the same number of points in each of them, right? So this is a residual plot. This is not the actual data, but this is a residual plot. So just plotting those distances away from the fitted value and the actual value, the observed value. But knowing that we're sort of looking at it this way too, we want to make sure that sort of all of the data points in there fall within one of the bins there, making sure that each one has about the same number, which in this case it does. So totally arbitrary the way that you draw the bins, but more or less just helping you sort of visualize this scatter. Well, what does poor scatter look like? What does unequal scatter look like? Well, it looks something like this. So these are still residuals. These are still residuals. The fitted value minus the observed value. And we see here, we kind of have this pattern, right? It looks like a bow tie, almost. This is not good. This is no good. We do not want this. We want to have equal scatter. We want to have everything sort of on the same plane, right? We see that here, though, it's like bunching up sort of in this area. It does look like a bow tie. I'm going to draw a little face. And then, as I'm doing this, take a look at the other one, too. The other one, it's the same kind of situation. We have some unequal scatter, but it's fanning downward like this, right? It's fanning downward. Not good, right? We want to have, in real life, we would want to have, I think, yeah, there we go. We would want to have data sort of all over the place, right? We want to have these residuals equally scattered. We do have ways of figuring out how to resolve this issue. We'll talk about that in just a little bit. But then we move on to our distribution of the residuals. And so remember that we're making sure that the goodness of fit is there. We're making sure that the straight line fits the data. And if that's good, then we move on to the equal scatter, making sure that everything is scattered equally across the plane there. And then we're looking at the residuals. So we have two options. We have, let me write in a different color. We have what's called a QQ plot, and then we have a histogram. So the histogram should be a little bit more familiar to most. I think it's easier to see the overall distribution rather than this QQ plot. Totally up for your own preference, but with this QQ plot, we want the residuals to fit on this line pretty linearly, right? So this is not the data, this is not goodness of fit, but this represents this represents a histogram, so you can plot it as such too, which we have on the other side. And this is also just a quick note, this is not the same data, these are not the same. Not the same. But then we can also plot the residuals, and we see here that it's sort of centered at 0 for the most part, and it has approximately a standard deviation of something, probably about 1, given that it's normal. So just keeping that in mind, you have two options, looking at the QQ plot, making sure that all of the data fall on that line, all of the residual data, I should say, fall on that line, or you can look at the histogram, sort of visually see how that distribution looks. And so this just a quick note, this histogram looks kind of funky in that it has sort of this guy out here and it's got this gap. If we were to change the bin size, probably would look a little bit better into slightly bigger bins. It definitely would look a little bit more normal in the English sense, normal, and then more normal in the statistical sense too. And here are some examples of non-normal residuals, non-normally distributed residuals. The QQ plot here has barely any of the points actually on the line that it draws there, so that's not good. And then we see over here sort of a right-skewed distribution, a right-skewed normal distribution. No good, right? If we were to maybe bin it differently, it probably would not look too different. But this is pretty sort of over there. Now, we do say, and I mentioned this earlier, that we do things in this order. 1, 2, and 3, right? Goodness of fit, homoscedasticity, and then the distribution. That also means that as you go down the list, you can be kind of liberal with how you are defining each one. And you can be okay with some level of imperfection, right? Now in this case, no good, right? This is not a good QQ plot. Again, not the same data here, not the same. So one thing before we move on, I mentioned earlier that we always do the assumptions and always do the checks in this order: goodness of fit, homoscedasticity equals scatter, and then the distribution, right? That also means that we can be kind of liberal with the amount of imperfection that we see in, these plots as we go down. Goodness of fit sort of is the most important, and we treat that one with the most importance. So just keeping that in mind, that we really care about the goodness of fit, because that's what regression is all about. But then when we're looking at equal scatter, there might be some hints of curvature or some hints of sort of fanning outward. But if it's small, right, if it's really small and that's up to your own judgment, then, that's fine. We can move on. And the distribution might look okay, right? Well, so we've talked about it for a long time. We've talked about what residuals are, but how do we do them in R? How do we make them in R? How do we see them? Well, we should be kind of familiar with it now, since we've worked with it in ANOVA, but we use the same ggFortify library. And it gives us this sort of 4-in-1 plot, sort of 4-in-1. And what that gets us is what we're sort of used to seeing, especially in the ANOVA world. Except with ANOVA, we sort of saw lines of residuals rather than the sort of equal scattering of them, or at least the more spread out version of it. But it's telling us the same thing, right? So we call in the library ggFortify, and then within that library is this function called autoplot, and you just put in your linear model. Pretty easy, right? Pretty easy, and it gets you this. It gets you this 4-in-1 plot. So there's a few issues that I have with this already. One, this background is sort of ugly. It sort of hinders a little bit the overall pattern, I think at least. If there is a pattern and it's subtle, it might sort of hinder that, or it might influence your eye to say, oh, maybe there's a pattern when it's not really there. And the same thing with this blue line here. Can be kind of misleading as far as curvature goes. So in this next slide, I add this smooth.color equals NA and this theme classic, and it gets rid of the background and it gets rid of the line. It gets rid of the line here. It will pop up with a warning saying that it's missing a bunch of values. That's because we're replacing them with this NA. It's not available here. So don't worry about that. Totally normal error, or totally normal warning message to get. But we're still working with the age and muscle density, right? Very gracefully written up there, and it looks something like this, right, with the points around it. And so this is the residuals for that data. And so we see some pretty equal scatter, right? We see that most bins that I've just drawn here most bins have the same number of points in each, so that's good. And we see and we see the QQ plot over here, and we see that not all of the points are on this line. This sort of indicates a little bit of skewness, but it's a little difficult to see that skewness just based on the QQ plot. And we also ignore these two. They're telling you the same thing, right? So this one's the most important, and then we can replace the QQ plot with a histogram, which is exactly what we're going to do. So if you look in the code, or if you want to do it yourself, you'll see that I have muscle, $resid. So this resid does not exist right now. Right now, our data looks something like this. We have our x and we have our y with all the values in each. And what I'm doing here is I'm saying, okay, make a new variable called resid. Make a new variable called resid. And then I use this function, resid, on our linear model, and I also get a whole new column of residuals for each observation here. Pretty sweet. So if we want to plot them as a histogram, we totally can. We see that they look something like this. So this is the GG plot histogram, and this is the base. This is a base R. The code is in the code that I give y'all on the class folder. So if you're following along, you'll see that both of these are there. This one, the base R histogram is easier to make, but it's a little harder to manipulate the bin size and everything. But the GG plot takes a little bit longer to code, only moments, but gives you more sort of free reign with how you can change things. And plus, we've got this nice light blue color filling in the bins here. So that's good. That's nice. So if we were to trace this, it looks something like that. In fact, it's actually, I guess, a little right skewed. So let me try to kind of get that here. Yeah. So it looks something like that, right? Where it's right skewed over here, we see the same thing, right? So with the histogram in base R, with the histogram in R, just in general, I should say, typically it's easier to make it with base R, just because you're probably not going to report that in your own research. More or less, it's just a diagnostic kind of thing. So you don't want to spend a whole bunch of time on it, unless you want to. But the base R is totally fine for the residuals. Of course, the GG plot, if you're looking at distributions of the actual data, not of the residuals, then the GG plot histogram looks a little bit better. So totally your call, but that's sort of my mindset. I use the residual, the base R for the residuals, and then I use, for everything else, I use GG plot. So just keeping that in mind. Okay, so here's a checklist. How do we do regression? What is sort of the roadmap for it? Well, I'll tell you. Just another great question from you. So first, we want to plot our dependent and our independent variable, or our predictor against our outcome. All right, so it looks something like that, right, in this case. And we can do that with ggplot. It's very easy to do it in ggplot, a little harder to do it in base R. Then once you do that, you sort of get an idea of how your data are behaving. So that's okay, it gives you some sort of impression on what your model is going to look like with the coefficients. And so then you make that model using our LM with our y as a function of x, where the data is the data equals data, and then you throw it in to the summary.lm function. Pretty easy, and it gets your coefficients and your p-values and everything like that, and then we check the assumptions 1, 2, and 3, goodness of fit, equal scatter, and the distribution of the residuals. We use that autoplot function out of the ggfortify library. And then we can look at the histogram just by using this hist for short, or histogram. And then we've just put in our resid model, or you can put in, if you're making a new column, you can just call your data, $, and then whatever you've called your new column. And then after that, you report your results. So you report, your regression equation, your regression formula, estimated formula at least, And then the p-values associated with the intercept and the slope, and then your interpretation for every 1 unit increase of x, y changes by whatever the beta 1 coefficient is, or beta k when we're working with multiple regression, multiple predictors. And then reporting whatever else you think is important. Some maybe number of outliers, the sample size, that sort of stuff. So just keeping that in mind, we will move on in the next video into confidence intervals and confidence bands. Very cool stuff. Stay tuned for that.